Okay, so I was already introduced. Thank you for the introduction, Juan Luis, and also I would like to thank the organizers for a very nice meeting and also a very nice program that made it possible for me to spend a month here. Very nice working environment, and it has always been nice weather when I've been here. I thought it was raining in England, but apparently not that rainy. Okay, so the thing I'm going to talk about is something I did together with Régis Monod, who's in Paris, called the Pont. And it concerns pointwise estimates to parabolic equation, and in fact the reason we were interested in this was primarily for the obstacle problem, the parabolic obstacle problem, but sort of as a warm-up I will try to talk about just the heat equation. Okay, so an outline of the talk, some introduction to what the questions we're interested in, then we'll try to describe the simpler setting for the heat equation, what happens there, and then I will do a sort of short introduction to the obstacle problem, maybe very short since we just heard a talk about the obstacle problem, and then describe what the differences are, and well, I guess maybe there will not be time enough for talking so much about the proof, but let's see. Okay, so the equations I'm interested in is the inhomogeneous heat equation, the first one here, or the parabolic obstacle problem. And if you feel very frightened by this right now, don't worry, I will come back to the obstacle problem and talk more about it later. So we're interested in this problem, and we're interested in the question if f, which is the right hand side here, is continuous in LP average, can we then say that the second derivative of u and the time derivative of u is also LP continuous in the average sense? Okay, and for the similar elliptic problem without the ut, this has been studied by Monod in an earlier paper, 2009, and I guess there are other results, especially in the elliptic case, that sort of gives you BMO estimates and similar things. So let's start with classical results for the heat equation. So if you study the heat equation with the right hand side, which is Dini continuous, and now I mean Dini continuous in the usual sense. It's continuous with a modulus of continuity, which is Dini with respect to the parabolic distance. Okay, so this is what you have, modulus of continuity with respect to the parabolic distance, and it's Dini if you can integrate the modulus of continuity with respect to 1 over r, and against 1 over r. Okay, then classical result states that the second derivatives of u in space variables and ut are continuous. And it's not so easy to find a very good reference from this, but here you have a couple of them, and I like very much the paper by Wang because it's a very simple proof using scaling arguments. It's very neat. Okay, and so what does it mean that d2u and ut are continuous? Well, in particular, for this problem, it means that you can write u as a Taylor expansion. So you have a linear part, and then you have a second order, well, parabolic second order polynomial, which is a solution of the heat equation with 1 as the right hand side, if you assume that the inhomogeneity has value 1 at the origin, let's say, and then plus higher order terms. So basically this gives you a Taylor expansion of second order. And remark here that when I say degree 2 or second order, I'm talking about parabolic second order, so it's degree 2 in space, degree 1 in time. Okay, so if you want to translate this, if the right hand side is just LP, and you know something more about the modulus of continuity in LP average, this is what we consider. So let's assume just for simplicity that the value is 1, and then you consider this modulus of continuity in LP averages, and maybe I should just mention that Q here is just a regular cylinder, so Qs is the ball of radius s, and then you take the negative time interval of order s squared. Okay, and then you take the averages over these cubes or cylinders, and we ask that this modulus of continuity is Dini. Okay? And what you can prove then, which I think is known, but I haven't found it anywhere in the literature, but I think this must be known since before, that if this is Dini, then you can write the second order Taylor expansion. So you have the second order expansion, which is a solution of the heat equation, right hand side 1, so that the difference between u and this polynomial has higher order than quadratic. Okay, so here we have divided by r squared, and you take the averages over the cylinders. And this decays to 0 with some speed. So we don't know the alpha, but some alpha. Okay, and remark that, so this is the second order Taylor expansion in LP averages, but if you take the equation of u minus this p and apply interior estimates, this implies exactly that you have VMO estimates of d2u and ut. And what's sort of different with this formulation, I would say, from what you can find in the literature, is that it's only at one point. So you only demand the information about f at a single point, and then you get exactly the information of the solution at that point. I think usually in literature you have that, okay, right hand side is in BMO, and then you get that the solution is in BMO, but it's not information at a single point. Okay, a couple of comments. So this is what I said, and some related results, but these are mostly in the elliptic case. So if anyone knows that this has been done classically in the parabolic case, let me know, because I haven't really found anything relevant in the literature.
You mean that estimate?
Yeah.
So that's DMO estimate with the right hand.
VMO.
Yeah, over VMO.
Well, yeah.
With the right hand side, which is exactly your modulus of continuity.
Yeah, but.
So that you can do with iteration, I think. This is the
Yeah, well, that's what. Yeah, exactly. That, yeah, you can, but I'm just, I think this must have been known since long time, but. Okay, so short introduction to the obstacle problem, which you have already seen. So obstacle problem amounts to that you have a string or a membrane that are attached at the boundary, and then you have some sort of obstacle that forces this to be pushed up. Okay, and so we've seen here where you don't touch the obstacle, the membrane is still free to move, so there it solves the equation. So if the relevant equation is Laplace equation, it's harmonic where you are above the obstacle, and at the points where you touch the obstacle, you're only allowed to do variation upwards, so there we have a super solution. So if you minimize this energy with a constraint that you're above an obstacle, you arrive at something satisfying this. So it's a super solution, it's a solution when you're above, and it's above. And of course with some boundary data, but I'm not really caring about the boundary data here. So this is one formulation of the obstacle problem. You can also formulate it, as we saw, as a variational inequality, which is equivalent. You can also take the formulation as the smallest super solution above the obstacle. Okay, but what I'm going to do here is you take the difference between this solution and the obstacle, and then you write the equation for that difference. So you look at the difference, and you see that when u is positive, that is when v is above the obstacle, Laplacian of u is simply minus Laplacian of phi, because there v is harmonic. So with a bit of work, you can show actually that the difference solves this equation. So it's sort of a normalized way of writing is Laplacian of u equals to some function times the characteristic function of u, positive. And for simplicity, and also for the reasons of proofs, people have assumed that f is not 0 at the point at the free boundary when they're studying. So, because otherwise you might have degenerate things. So let me just draw a simple picture that we actually saw the other day from Pablo. So you have a set here where u is positive, and then you have a set here where u is 0, and a set where u is positive. You have that u solves the equation Laplacian u equals to f. And then here, this is the free boundary. So this is what makes it possible for me to be here, that there's a free boundary, right? Okay, so, but I'm going to talk about the parabolic version of this. So I will just consider this problem, and you can arrive at this formulation as well if you consider the least super solution to the heat equation that are above an obstacle, and then you take the equation for the difference between the obstacle, between the solution and the obstacle. Okay, so the parabolic problem is related, of course, to the Stefan problem, but then you have additional information on the time derivative. It has a sign. You can also think of this as a model of heat diffusion in a container, where you have some device that try to force the solution to go down whenever it's above zero. And it's also somehow related to pricing of certain options, but usually in finance you have a more complicated equation. But at least if you want to understand those equations, it's probably better to understand this first. So like I said, this boundary here is the free boundary. So let's put a UT here. So this is the equation, the problem. Okay, so what are we interested in here? Well, since we have one set where we have a nice equation, we would be very happy if this free boundary was regular, because then we can just solve the equation and apply boundary estimates and everything. Unfortunately, life is not that simple, so you have to understand how does this free boundary behave. It can behave badly, it can behave nicely. So the properties of U around free boundary points are essential. Okay, in particular the optimal behavior or the optimal growth around these points. And also the behavior of the free boundary. And the question is, of course, is it regular? And at least in the elliptic case, there's a counterexample where you actually have cusp singularities, as probably most of you know. And there's also a counterexample in the elliptic case where you have F here. If F is not Dini, then you can always construct free boundary points where the free boundary has an infinite spiral sort of going in. So you might have, the free boundary might not behave that nicely. And also due to this, that you might have singularities or spirals. If you want to obtain a similar Taylor expansion for this problem, it's slightly different because, well, for the heat equation, there's going to be one polynomial that sort of determines the second order behavior of the solution at one point. But for this problem, they might be different. So you have, if you want a Taylor expansion, you have to sort of distinguish at which kind of point are you, and then after that obtain the asymptotic behavior. So typically a singularity would look like this: a cusp where the zero set is small or thin around the free boundary point, and typically like a regular point will be something like this. And what you expect, this is in the simplest case, in the elliptic time independent case, that if you zoom in infinitely, I will try to explain a bit more about the zooming in. If you zoom in here, the free boundary will straighten up if it's C1. So you will obtain asymptotically, you would expect you have positive solution in half space and zero in the other half space. And if you're at a singular point, the typical behavior in the time independent case would be that you have positive in one half space, positive in the other one, and zero in between. So these are the two typical behavior that you have to sort of distinguish in between. So let's try to just explain a bit this zooming in procedure. So it's fairly easy and standard by now to prove that the second derivatives of U and UT are bounded. I'm not going to go into much more than that, but for instance, there's a paper by Henrik, Arshak Petrosian, and Louis Caffarelli, where they do this for a more general problem. So if you have that the second derivative, the second spatial derivatives are bounded, then UT are bounded, then you have quadratic growth in the parabolic setting, scaling. around free boundary points. So this means that if you consider these rescaled functions, these will remain bounded if you have this estimate. Okay, so the idea is now to consider these rescaled functions and look at what are the possible limits of these as r goes to 0. Okay, and you can just see that the equation is more or less invariant under this scaling, except that you will get an r inside the f here. So when you let r go to 0, this f will just become f of 0, which you have all the time assume is 1. So the limiting equation for these guys will be just this obstacle type problem, but with a 1 in front of the characteristic function. Okay, so this is exactly what I meant when I said zooming in, studying these limits. So if you're able to classify all these limits, you obtain a lot of information about the behavior of the free boundary there. So like I said, it's not in general unique, since you might have these spirals going on, and then you will have different blow-ups depending on which subsequence of these radii you take.
If we degenerate at 0, we get act like integration.
Right. So if f happens to be 0, yeah, then it's a different problem. So that's why, for that reason, we assume that f is 1 at the origin. So you will get a 1 there. Otherwise, it's much harder, different. Then you have to ask Karen. That's what he's doing. Okay, so in the more complicated setting then, in the parabolic case, we can distinguish between regular points, which are exactly when these blow-ups, this u0 is of this form. So you have x1 squared, the positive part of some coordinate squared over 2. And these are sort of the good points that corresponds to, you have a smooth curve representing the free boundary, and then you will obtain this. And the other part that's usually referred to as singular points, then you will obtain polynomial type solution, well, with certain restrictions of the coefficients so that it's actually solved the problem. So if we want this, so when I'm supposed to stop?
You still have more than 5 minutes.
Oh, more than 5 minutes. Okay. So if we want to obtain a Taylor expansion, we have to distinguish between these 2 points. Because if we're close to these points, we expect that this is this asymptotic behavior. And if we're close to these kind of points, we expect that solutions like this are the asymptotic behavior. So it's slightly different if you just have, from the case when you just have an equation. And just some comments on these free boundary points. There are several ways of distinguishing if you're close to a regular point or a singular point. There is one which is usually referred to, well, some people call the Caffarelli alternative, which more or less amounts to checking if the 0 set is large enough at small scales. So either you can do it with the Lebesgue measure, or you can do it with so-called minimal diameter. And if the 0 set is large enough at small scales, then you will be at a regular point. And then there's another way of doing this, which is an wise energy approach. As you can write an energy functional. This also works for the elliptic case. So basically you have the Dirichlet energy plus something corresponding to a boundary term. And it turns out that this energy here is almost monotone. So it's the derivative with respect to r is bounded from below. So this means that this has a limit when r goes to 0. And the limit of this functional determines exactly whether we are at the regular point or a singular point. So it has the minimum at regular point, which, well, if you have normalized everything, and I had done, so you have 15 over 2, and at singular point, the value will be 15. Okay, so a couple of known results. Well, there's one that I mentioned, Caffarelli, Petrosian, and Shogolian, that treats this problem when f is equal to 1. And then there's a series of papers by Blanchet, Dolbeau, and Monod, treating this with variable coefficients and also variable right-hand side, not obtaining exactly the sharp results, but almost. And then they studied the singular set and also the regular set. And in the elliptic case, more or less everything is well understood, except for the case when Farid was mentioning when f can be 0, then basically nothing is understood, I think. So what we can prove is that if you're close to a regular point, then you have this Taylor expansion in LP average, assuming that this modulus of continuity is Dini. And if you're close to a singular point, you also have this Taylor expansion. And at singular points, we're actually forced to assume that the sigma is double Dini, which means that you can integrate it against 1 over r twice. Otherwise, well, things doesn't work. So in particular, if you assume that f is continuous, using these expansions, you can obtain that near regular points, the free boundary is C1, it's a C1 graph in the parabolic setting, and that the singular set is contained in either a graph where t depends just on the spatial variables, or in a parabolic C1 manifold, actually of different dimension depending on the blow up, but you can always put it in a manifold of dimension m. And well, due to the counterexamples in the elliptic case, at least the first result is sharp, because if it's not Dini in the elliptic case, you can construct these spirals. And concerning the second result, I don't really know, but I think in the elliptic case, this is more or less what you know in the elliptic case, and maybe something more is known. I don't really know what should be the optimal result there.
The double Dini is because of monotonicity?
Right, so we use Monod's monotonistic formula, so yeah, that's why we need it. Okay, so I think I'm running out of time, so let me just say a couple of words shortly about the proof. So the proof we do is a linearization technique. So basically we look at the linearized problem around a blow-up limit. So you get an equation for that, and for that you can prove Liouville type theorems that allows us to conclude this. And essential tools for the singular points here are, like I said, the Weiss monotonistic formula, and also a different type of formula that was introduced by Régis Monod type formula. And these two are very essential. So I would say you can, for singular points, you can use a monotonistic formula of Alcafarelli type, but that demands more about the regularity of the right-hand side. Or you can use this Monod type formula, and then you can treat at least slightly worse right-hand side. Okay, I think I will stop there now. Thanks.
Any questions? So if f0 equals -1, is the problem still well posed?
Say what?
f0
Yeah.
equals -1.
Yeah, that's a completely different problem. But there's Henrik has a couple of papers about this problem. But it's very different, and you will not get in general the quadratic growth. You will get something else. So
You get usually crosses. Free boundary is not, you have to look for crosses.
and I guess it's not stable, so you don't have a unique solution either for that problem. So. It's completely different. Yeah.
So these problems are like obstacle formulations of Stefan problem, right?
Right.
So in the case with F, it has the opposite sign, looks like undercooling.
It's the composite membrane.
Yeah.
So they come from a very different area.
Just going back to the classification of global solutions, so I said that if you have a polynomial depending on t, if your global solution is that has that linear part in t, then that means that you have a singular point.
Yeah.
So what's the kind of what's the heuristic explanation for that? Because still you have very nice surface, right? So
Yeah. So the free
so you have for stationary one which doesn't depend on t, right? You have
Yeah.
regularity. So why this T dependence kind of damages the regularity.
Well, it doesn't damage really. I mean, if you take anything of this form, I mean, forget about the T and take this, then the free boundary, well, you don't know what it looks like.
Okay, so you don't have plus sign there. All right, okay. You have a maximum of the product there. Okay, yeah, sorry.
So yeah, I mean, well, one thing that you should say as well is that from the monotonicity formula, you can say that the set of regular point is an open set in the topology of the free boundary. So I mean, so you might have singular points that are just points, and then I guess it's hard to say what the dependencies.
The regularity you obtain is better for
Speak
electric
louder,
case.
please.
Sure. Yeah. The regularity you obtain for each t, what is, I mean, can you pass the limit when t goes to infinity to obtain? Because
So I guess all our estimates are actually local in times, but yeah, maybe one could do that. But more or less, those results are already known for the elliptic case. So.
you here gain more regularity, of course.
Huh?
In parabolic case, you obtain more regularity.
No. I mean, these results are known for the elliptic case, so you wouldn't actually get something more. Yeah.
Thank you.